So let's look at Prim's algorithm for computing a minimum cost spanning tree in a graph. So as we said, the greedy method suggests that we start with the smaller edges and go to the bigger edges. So Prim's algorithm will start with the smallest edge. So we begin constructing our tree with the smallest cost edge in the entire graph. And what we will now do is that we will extend the current tree using the smallest cost edge that can connect to it. Right? So this is the greedy strategy. So at each point we have currently a partial tree and we extend it in the minimum possible way by adding the smallest edge which can be used to extend the tree. So let's look at an example. So here is a graph with 7 vertices numbered 1 to 7, and the blue labels on each of the edges indicate the cost of these edges. If we examine the cost, then we find that the minimum cost is 10, and that's the edge connecting 1 to 6. So Prim's algorithm would begin by considering this to be the initial edge in our tree. Now we have a tree connecting 1 and 6, and we look for the smallest edge that we can use to extend this tree. Now there are only two edges which you can consider, either 1 to 2 or 6 to 5, because all the other edges are not connected to this current tree. So among these, 25 is smaller than 28, so we will extend 6 to 5 as a new edge, and now we have a tree containing two edges. Now we have to look for all edges which can connect to this new tree. So we have a choice between 1 to 2, which we already had, and 5 has two outgoing edges, to 7 and to 4. So we have among these three edges, 28, 24 and 22, we pick the minimum one. So this gives us clearly the edge 5 to 4, because 22 is the smallest of these three numbers. Now we have to construct a tree which connects this tree to the rest of the network. So we again have 1 to 2 in consideration. We have 5 to 7 in consideration. We have 4 to 7 and 4 to 3. All these are possible ways of extending this so that we have a tree. So notice that we want to keep a tree, so the new node has to be outside. We cannot go back and construct an edge going back into the tree, because that would violate the tree property. Right? So if we look at these, we have a choice between 28, 24, 18 and 12. And so we choose the smallest one, which is 12, and then we go here. Okay? And now again we do the same thing, and we find that we have a choice between 28, 24, 18 and 16. 14 is not yet in consideration, because 14, neither endpoint is in the tree. So if you look at this tree, then 16 is currently the smallest one, so we will add this. And now we have a choice between 28, 14, 24 and 18. And so since 14 is now the smallest, we will connect it this way. And so we have a spanning tree which is formed by the red edges, and this is the one that Prim's algorithm will construct. Notice that in this particular example, all the edge weights are distinct. No two edges have the same weight, and so actually there is only one unique spanning tree, although we will not prove it here, but there's only one unique spanning tree, and the claim is that Prim's algorithm will find this unique spanning tree. Now, as we said before, if we don't have unique edges, then we may not have a unique spanning tree. Now, how does this come in Prim's algorithm? So let's go back to our example before. So remember that we had this graph where the top and the bottom had the same weight, and the left and the right had the same weight. Now there are two situations where Prim makes a choice. The first is in the initial thing. You have to pick up the minimum cost edge. Now there are two edges with minimum cost. So we can either start with the left or the right. So if we start with the left, then we have this, for example. And now we have to pick the smallest edge that can extend this tree. So if we pick this, we can either pick the top or the bottom. So if we pick the top, then we will go this way. And then we again have to pick the smallest edge which will extend the tree. Now we have no choice. So we would pick the right edge and we will come here. So this is one tree that our algorithm will construct. On the other hand, if we again started from the left, right, then at this point, if we pick the bottom edge rather than the top edge, because we have to pick the minimum cost, but there are two choices for extending the tree with the minimum cost, then we would pick this edge, and then again we would pick this edge. And so we would get the two trees that we constructed by hand as two different ways of executing Prim's algorithm. Of course, when we implement the algorithm, we would make a canonical choice whether to choose this one or this one. Maybe we will number the vertices and pick the vertex which is smaller. But in general, Prim's algorithm will produce different spanning trees depending on the strategy used to break ties between equal length edges. So we can have situations where Prim's algorithm will give us a different spanning tree depending on how we implement it. So to implement Prim's algorithm effectively, we need to be able to compute the smallest edge extending the tree. So the way we will do this is the following. So for every vertex I, we will maintain a quantity which we will call near of I. Now there are two possibilities. So if I is in the tree already, then we are not interested in adding it. So we will just put near of I to some dummy value, let us say 0. So near of I is supposed to be another vertex. Okay. If I is not in the tree, okay, then if near of I is equal to j, this means that j is in the tree and ij is the lowest cost edge from I to any vertex in the tree. In other words, I can be connected to this tree in possibly many different ways, but the best way to connect I to this tree is to use the edge ij, because among all the ways that I can be connected to the tree, ij is the smallest edge. So now let us see what happens when we try to extend the tree. So we look at this edge I near I for each I which is not in the tree. Right? And then among these, we pick the minimum one. And having picked this, now we will add the specific edge that we picked, which is I near I, to the tree. So now I belongs to the tree, so we update its near value. So we set near of I is equal to 0 to indicate now that I belongs to the tree. Now, what happens to other vertices k outside the tree? Okay. So for such vertices, we had possibly a pair k near of k, which is the best edge to the old tree. So to this, we have to compare the cost of the edge from k to I, because now I has been included in the tree. And if this is smaller, then we update near of k to be equal to I. So now there is a better way to get from k into the tree by the new vertex I which we have just added. So with this, let us take a look at the pseudocode for Prim's algorithm. Okay, so here is the pseudocode for Prim's algorithm. So Prim's algorithm takes as input the set of edges, then cost, which gives the cost of the edges, n the number of vertices, and t is going to be the tree that the algorithm builds up. Now for simplicity, what we assume is that cost, rather than explicitly giving cost to edges, actually is a matrix which has, so remember the vertices are 1 to n, so it is a matrix of 1 to n to 1 to n, right? So now the cost of the edge ij is just the ijth entry in this matrix. And in particular, there may be no edge ij, so this is infinity if there is no edge. Right? So this is the assumption about cost. Right? So this is how the initial parameters are defined. And now we look at how the algorithm actually works. So we begin, as we said, by choosing the smallest edge. Right? So we pick some two vertices k and l such that this edge is the minimum cost edge in our graph, and we initialize our tree to this. So we have t. So t is going to be a two-dimensional array. So it's going to have the endpoints of the edges in our tree as the first and second columns. So t11 is set to k, t12 is set to l. And we also keep track of the minimum cost of the tree we have built up so far. So we initialize this minimum cost of the cost of the edge we have just added. Right? Now what we have to do is set up this near information. So we pick up any vertex I which is outside this tree, and we compare the cost of these two edges, right? So let's assume that both the edges exist. Then if the cost of I to L is smaller than the cost of I to K, then we set near of I to be L. On the other hand, provided there is an edge from I to K, then since it has a smaller cost by this check, then we set near of I to K. Now there is a possibility that there is no edge in between I and J at all, I and K or I and L. So we have K, L, and I is a completely disconnected thing. And so we will assume that near of I is equal to -1. We can also take near of I is equal to infinity and work with that, but it's a bit of a mess. So we will use -1 as a special signal to say that I is currently not connected to any part of the tree. And having said all this, we now have to, of course, initialize that for the vertices already in the tree, the value is 0. So near of K and near of L are both set to 0. Now we run through the remaining vertices exactly as we had described informally before. We choose that J such that there is a positive value, so it's outside the tree, okay? And so if it is greater than 0, it's not -1 also. It is connected and it is not in the tree. And we find that its cost among all such J is minimum. Having identified this, we will now add this as our new edge. So we will now say that the ith edge has endpoints J and near J. The minimum cost is increased by the cost of this edge. And now we have to update the near values. So the first thing we do is we set the near value for the newly acquired vertex to be 0. And for every other vertex, if it has a positive value, that is, if it is connected to the tree already, and its cost that is already connected with is more than the cost of the edge from K to J, or there was no connection, right? So earlier it was not connected to the tree, but now there is an edge from K to J. In either of these cases, we will set near K equal to J. So in this way, for every new iteration, we will pick up one more vertex to connect by looking at that vertex which can be connected using the minimum cost edge among all those that can be connected. And in the end, after n-1 steps, we would have added all the remaining vertices. And so we will have a spanning tree and we will return the minimum cost. And the tree itself is accumulated in this argument T. So we should note that the algorithm that we have presented here is slightly different from the one given in the book. So the main difference in the book is that this possibility that near of I is actually equal to -1 in case there is no edge from I to the tree is not considered. So what happens in the book is that, for instance, when you start with the edge KL, you first check whether the cost to L is less than the cost to K. If so, you set it to L. Otherwise, you blindly set it to K. So now there are two possibilities. There is an edge from I to K, which is the good case. But if there is no edge I to K, you will still get near of I assigned the value K. Okay, so there is a spurious possibility that near of I is pointing to K even though there is no edge. Now the reason that this is not a problem in the long run is that eventually you will actually check whether the cost of this non-existent edge is minimum, and if there is no edge, the assumption is the cost is infinity, and so it will never be the minimum. So the book does not explicitly take care of the situation that I is not connected to the tree, but overall, if you look deeply into the code, it works out. We try to make it explicit by adding the separate case that near I is equal to -1. And this also, if you don't have this -1 case, then you will check, if you go back, that this particular update is also slightly simplified. So you can compare this line from the textbook to the code that we have presented in the previous slide. So we can actually simplify Prim's algorithm using the following lemma. So the lemma says, let E be some minimum cost edge incident on, that is attached to, vertex B. So pick any vertex and pick any minimum cost edge attached to it. There may be more than one. Now the lemma says that there is some spanning tree of course minimum cost that contains E, right? So we pick any vertex and we pick any minimum cost edge E, then there is guaranteed to be a spanning tree which contains that minimum cost edge. So how do we use this? Well, we'll prove this separately in a different module, but let's assume this lemma. So how do we use this? So now we need not start the tree with the smallest edge. Instead, we can start at any arbitrary vertex v that we would like, right? So we have initially a tree which contains just v. So this is a trivial tree with one vertex and no edges. And what we would do in the first step is that we would actually end up, as we normally use Prim's algorithm, we'll actually end up picking a minimum cost edge at v to start the tree. Right? So this need not be, the point is this need not be a global minimum. This is a minimum cost edge at v. So the new algorithm looks similar to the old algorithm. We start with the edge set, the cost matrix, the number of vertices, and t, the tree we're trying to build up. But now we initialize our cost to 0, right? And we are assuming that 1 is our first, so we're going to start with the vertex number 1. So this is going to be our initial tree. So initial tree has only one vertex and 0 edges. So for every other vertex, if it is connected to 1, okay, so this should be a small I. If it is connected to 1, then we set near of I equal to 1. Otherwise, we say it's not connected to 1, so we set it to minus 1. And because 1 is in the tree, we set near I to 0. Now we do the same thing for every vertex starting from 1 to n minus 1, because we don't have it. Earlier we did 2 to n minus 1 because we already started with 2 vertices. Now we start with one vertex. We do exactly the same thing. We choose the smallest j which is connected to the tree with a minimum cost edge. In particular, initially the first time it will pick among all the neighbors of 1, it will pick one of the minimum cost edges. Right? And it will start by extending 1 to a tree which involves 1 and the nearest neighbor of 1, and it will continue in this way. So the rest of it is the same as the original algorithm, and we will return the min cost in the end as before. So what is the complexity of Prim's algorithm? Well, we have an outer loop that runs n times. Well, actually it runs order of n times, because it actually runs n minus 2 times or n minus 1 time, depending on whether we're using the first version or the second version. And inside the dominant cost in each iteration is to scan these pairs I near I to find the minimum. Right? So in the worst case, we will generally be scanning n vertices. Of course, the number will keep coming down. So it's clear that this is order n, that is order n. So overall, we have an O n squared upper bound. And this is the basic cost of Prim's algorithm. So to improve the efficiency, we need a good data structure for keeping track of near I. So we need a data structure for and this data structure should allow us to quickly look up the minimum element, remove it, and do all the updates that we had before. So it turns out that a good candidate for this is what is called a red-black tree. So we'll organize a red-black tree in terms of the costs of the edges connecting I. And what this red-black tree allows typically is it allows insert, okay, then it allows finding the minimum, it allows deleting an arbitrary value, and it allows adding, insert is already, it allows searching for an arbitrary value. So this is the general properties of a red-black tree, and all of these can be done in time logarithmic in the size of the tree. So in each iteration, what we do is we keep these values near I organized by cost of the edge I comma near I. So when we want to find the next edge to add to our tree, we will find the minimum. Then having found it, we will delete it from the tree. Now we will look at all the neighbors of the edge that we have, vertex that we have added, and we will search for them in this tree. Then we'll compare that value to the value of the edge connecting this, and depending on that, we might delete that value and insert a new value. Right? So all these operations are logarithmic values, and there are a fixed number of them that we do at each point. It only depends. Remember that we do this edge update, that is updating the near value exactly once for each edge. So every time we add a vertex, we only have to look at its neighbors. Right? So the total number of updates that we do to this near value, okay, is once for each edge in E, because when we add a vertex, right, we have to update only those edges which are incident on that vertex, and we will never look at that edge again because it will never be incident on any other vertex which comes into the tree. So given this, it turns out that we will have to do, of course, our old n log n operations to find the minimum, etc. And we will have to do, so if the size of the edge is typically denoted by m, we'll have to do m log n operations overall to update the near values. So this gives us a total complexity of order m plus n log n, right? So now one thing to keep in mind is that m could be order of n squared, right? So if m is order of n squared, then this becomes n squared log n, which is worse than what we had in the naive implementation without red-black trees. So red-black trees will help, provided our edge set is small enough that m is, say, of order of n, then we'll get an n log n algorithm instead of an n squared algorithm. If we have a lot of edges in our graph, then it doesn't really matter. Red-black trees don't help, and we may as well go ahead and use the naive thing where we just scan through all the near values in order to determine the minimum. Okay. So in summary, we have found one greedy implementation of the minimum cost spanning tree. Okay, and this is Prim's algorithm. And the naive implementation takes O(n) squared, and we can improve this to m plus n log n if we use red-black trees in order to keep track of this near information which is used in order to extend it.